Again, welcome to Operating System CS332 class. In these lectures, we're going to cover the virtual memory in an operating system course. So our main objective is to understand the concept of locality and virtual memory, also paging and segmentation, and also protection and sharing of, again, memory, virtual memory. So before we start, we will go through some few virtual memory terminology. First, what is a virtual memory? So here we say a storage allocation scheme in which a secondary memory can be addressed as though it were part of the main memory. The addresses a program may use to reference the memory as distinguished from the addresses the memory system uses to identify physical storage sites. And also program-generated addresses are translated automatically to the corresponding machine address. So the size of a virtual storage is limited by the addressing scheme of the computer system and also by the amount of secondary memory available and not by the actual number of the main storage locations. So we can see that, as we all know, in a computer system, the CPU only can get access to data and programs from the main memory. So the concept of virtual memory really enhances the efficiency of computation. Because, for example, if we have a main memory of a computer system and the size is, let's say, 3 megabytes, and I have a program and the data which is over 3 megabytes, this means I cannot run the program or I cannot open the data in my computer system because the memory is not enough. So the concept of virtual memory means we are going to use some of our secondary storage device, such as the hard drive, part of it as a memory. So the computer will see a secondary device, storage device, as a primary storage device or main memory. So this again will enhance our computation. Also, we have the term virtual address. Here we say the address that is assigned to, again, the term virtual means it's something that is not existing, but it looks or it feels like it exists. So again, virtual address will be the address assigned to a location in virtual memory to allow that location to be accessed as though it were part of the main memory. And also virtual address space will be the virtual storage that is assigned to a process. And address space will be the range of memory address that is available to a process. And now the real address will be the address of the storage location in the main memory, or I would say the physical address. So that's the difference. There's difference between the virtual address and also the physical address. So the physical address will be the actual address of the storage location in the main memory. But the virtual address, again, will be the location in the virtual memory that is part of the secondary storage device. So again, so those are the 5 terms. So I think we can start with the concept of hardware and also the control structures. Now, comparing simple paging and also simple segmentation, on the other hand, also with a phase and also dynamic partitioning. We know a phase partitioning means we allocate or we partition either the hard drive or memory at a specific size. And dynamic, that's before running the program. Dynamic partition means during the execution of a process or a program, then we partition. So here we are going to compare a simple paging with a simple segmentation with a phase and also dynamic partition on the other hand. We see that the foundation for fundamental breakthrough in memory management. So the two characteristics of paging and segmentation are the case in this breakthrough. One, all memory references are logical addresses that are dynamically translated into physical address at runtime. So this means that a process may be swapped in and out of memory such that it occupies a different regions of the main memory at different times during the course of execution. The keyword again is dynamically translated. And the second is a process may be broken up into a number of pieces that don't need to be contiguously located in main memory during execution. So the combination again of dynamic runtime address translation and also the use of page or segment table will permit this. So again, if these two characteristics are present, it is not necessary that all of the pages or segments of a process may be in the main memory during execution. And so these two concepts lead us, or basically the concept of virtual memory. So next is the execution of a process. Let's say for now, we can talk in general terms, and also we will use the term pieces to refer to either page or segment, depending on whether paging or segment is employed. Now, suppose that it is time to bring a new process into the memory. Again, the memory operating system, the operating system begins by bringing in only one or few pieces to include the initial program piece and also initial data piece to which those instructions refer. Now, the portion of a process that is actually in a memory at any time, again, is defined to be the resident set. And also, as the process executes, things proceed smoothly as long as all memory references are to locations that are in the resident set. Now, using the segment or page table, the processor always is able to determine whether this is so. Now, if the processor encounters any logical address that is not in main memory, then it's going to generate an interrupt, which indicating a memory access fault. So the operating system puts interrupted process in a blocking state. Now, for the execution of this process to proceed later, the operating system again will need to bring into main memory the piece of the process that contains the logical address that caused the access fault. Now, for this purpose, the operating system issues a disk I/O read request. And now, after the I/O request has been issued, the operating system then can dispatch another process to run while the disk I/O is performed. Now, once the desired piece has been brought into main memory, an I/O interrupt is issued, giving control again back to the operating system, which places the affected process back into ready state. Now, we know there are two implications. There are two implications here. The second more startling than the first, and also both lead to improve the system utilization. So again, the first is the more process may maintain in memory. And here, because we are only going to load some of the pieces of any particular process, there's a room for more processes. So this will lead to more efficient utilization of the process, because it is more likely that at least one of the more numerous processes will be in ready state at any particular time. Secondly, then a process may be larger than all of main memory. So again, this is one of the, I would say, advantage of the concept of virtual memory. As we said earlier, if we have a program to be open or a program to be run and our main memory size is less than the program size, it means we cannot run this program. And even if we can run it, it will be very slow. So that's our second implication. The process may be larger than all of the memory, and that will be fine. So this is one of the most fundamental restriction in programming is lifted. And the most fundamental restriction in programming is, again, you have a program or a data that is larger than the main memory. Either it's going to run very slow or it cannot run at all. So virtual memory make this possible to be lifted or to be solved. So without a scheme, we have been discussing a programmer must be acutely aware of how much memory is available. If the program being written is too large, again, the programmer must devise ways or must provide some ways to structure the program into pieces that can be loaded separately in some sort of overlay strategy. Now, with virtual memory based on paging or segmentation, that job is left to the operating system and also the hardware. As far as the programmer is concerned, he or she is dealing with a huge memory, the size associated with this storage. So the operating system automatically loads a piece of a process into main memory as required. So here the real and the virtual memory. Now the real memory is the actual memory or the main memory. Then the virtual memory normally is a memory in our secondary storage device, such as the disk or hard drive disk. And this allows for effective multi-programming and also relieve the user of tight constraints of main memory. So virtual memory again improve or again enhance the size of the real memory. So the table here will summarize the characteristics of paging and also segmentation, either with or without the use of virtual memory. So we can say simple paging, virtual memory paging, then simple segmentation, virtual memory segmentation. So here we say the main memory partition into small face size chunks, which we call the frames. That's for paging. Now for segmentation, the main memory is not partitioned. With paging, again, is partitioned into small size called the frames. Now the program broken into pages by the compiler or memory management system in terms of paging or simple paging. But in terms of segmentation, program segment specified by the programmer to the compiler. And this means the decision is made by the programmer. No internal fragmentation in terms of segmentation. In terms of paging, there is internal fragmentation within the frames. Also, paging, no external fragmentation, but segmentation, there is external fragmentation. Operating system must maintain a page table for each process showing which frame each page occupies. Now with segmentation, operating system also must maintain a segment table for each process showing the load address and also the length of each segment. Also, the operating system must maintain a list of free holes in main memory. But with paging, operating system must maintain a free frame list. Also, the processor uses page number offset to calculate the absolute address in terms of paging. Now, in terms of segmentation, the processor uses the segment number, then offset to calculate the absolute address. So the next we will talk about the concept again of trashing. Now, to understand what the key issue is and why the virtual memory was a matter of much debate. Now, let us examine again the tasks of operating system with respect to virtual memory. Now, if we consider a large process, which consists of a long program plus a number of arrays of data, over any short period of time, execution may be confined to a small section of the program. Example would be a subroutine. And access to perhaps only one or two arrays of data. Now, if this is so, then it will clearly be wasteful to load in dozens of pieces for that process when only a few pieces will be used before the program is suspended or swiped out. Now, we can make a better use of memory by loading in just a few pieces. Then if the program branches to an instruction or references a data item on a piece not in a main memory, then a fault is triggered. So this tells the operating system to bring in the desired piece. Thus, at any one time, only a few pieces of any given process are in memory, and therefore more process can be maintained in memory. Further, also, time is saved because the unused pieces are not swiped in and out of memory. However, the operating system must be clever about how it manages this scheme. Now, in the steady state, all main memory will be occupied with process pieces. So that processor and operating system have direct access to as many processes as possible. Now, when the operating system brings one piece in, it must throw another out. Now, if it throws a piece just before it is used, then it will just have to go get that piece again almost immediately. Now, too much of this will lead to the condition that we call the trashing. So a state in which a system spends most of its time swiping process pieces rather than executing instruction. To avoid this, the operating system tries to guess based on recent history which pieces are least likely to be used in the near future. So again, the concept of trashing is when the operating system keeps swiping process pieces rather than executing it. So that will lead us to the concept of principles of locality. So the reason is based on belief in the principles of locality. And we discussed about principles of locality in our first lectures. To summarize, the principle of locality states that program and data reference within a process tend to cluster. Hence, the assumption that only a few pieces of a process will be needed over a short period of time is valid. Also, it should be possible to make intelligent guesses about which pieces of process will be needed in the near future, which avoid the concept of trashing. And so the concept of principles of locality is to, again, avoid the trashing method. And as we said, trashing means instead of the operating system to execute processes, it's rather swapping processes often. So here we say support needed for virtual memory. Here again, the principles of locality will suggest that a virtual memory scheme may work. Again, principles of locality, the whole concept is to avoid the trashing issues. Now, for a virtual memory to be practical and effective, two ingredients are needed. Again, for a virtual memory to be practical and effective, two ingredients are needed. First, there must be a hardware support for the paging and or segmentation scheme to be employed. And secondly, the operating system must include software for managing the movement of pages and or the segments between secondary memory and the main memory. Now, the term virtual memories is usually associated with the system that employed, again, paging. Although in virtual memory also is based on segmentation. And the use of paging to achieve memory was first reported for the Atlas computer and soon came into widespread commercial use. Now, in the discussion of simple paging, we can indicate that each process has its own page table and all of its pages are loaded into main memory. The page table for a process is created and loaded into main memory. So each page table entry contains the frame number of a corresponding page in main memory. And also a page table is also needed for virtual memory scheme based again on paging. So the basic mechanism for reading a word from memory involve translation of virtual or logical address, consists of a page number and offset into a physical address consisting of frame number and offset using the page table. So we can see from our diagram, we have the page table here, the virtual address with the page number and its offset, which must be translated into a physical address with the frame number and offset. And also getting the frame number from the page table with its register. And this is the paging mechanism, the program. Then in the main memory is loaded, we have the page frame in the main memory to offset it. Now, because the page table is of a variable length, depending on the size of the process, we cannot expect to hold it in registers. Instead, it must be again in the main memory in order to be accessed. So this diagram suggests that the hardware implementation is again address translation paging system. Now, when a particular process is not running, a register will hold that starting address. The register will hold the starting address of the page table for that process. Now, the page number of a virtual address is used to index that table and look up the corresponding frame number. So get the corresponding frame number. Then this is combined with other offset portion of the virtual address to produce the desired real address. So the diagram here also shows again an example of a two-level hierarchy page table. This normally used with 32-bit address. So if we are assuming byte level addressing, then a 4K kilobyte pages. Then the 4 gigabyte virtual address space composed of 2 to the power 20 pages. 4 gigabyte. Now, if each of these pages is mapped by a 4-byte page table entry, we can create a user page table composed of 2 to the power 20 page table entries, which require 4 megabytes. That's 2 to the power 22. Also, this diagram shows steps that is involved in address translation for the skin. So translation of, we can see in a two-level paging system. So the root page always remains in the main memory. So in the main memory, we may have the root page. And the first 10 bits of a virtual address are used to index the root page to find the PTE, which is the page table entry for a page of the user. Now, if that page size is not in memory, it's not in the main memory, then the page fault occurs. But if that page is in the main memory, then the next 10 bits of the virtual address index into the user page table entry page, or the PTE, to find the PTE for the page that is referenced by the virtual address. Now we have a drawback here, and the drawback of a page, or the drawback of the type of a page tables that we have been discussing, is that their size is proportional to that of the virtual address space. So an alternative approach to the size of one or multiple level page tables is the use of, again, the inverted page table structure. So variations on this approach are used on the PowerPC UltraSparks architecture, and also an implementation of Mac operating system on RTPC also use this scheme. So in this approach, again, the number portion of virtual address will be mapped into a hash value using a simple hashing function. Then the hash value is a pointer to the inverted page table, which contains the page table entries. Now there's one entry in the inverted page table for each real memory page frame, rather than one per virtual page. So here, a phase proportion of the real memory is required for the tables regardless of the number of process or virtual pages supported. Now, because more than one virtual address may map into the same hash table entry, the chaining technique is used for mapping the overflow. Now, inverted page, here we say that each entry in the page table include the following. We have the page number, the process identifier, control bits, and also the chain pointer. So the process identifier, that is the process that owns this page. And it will be the combination of page number and process identifier, normally identify a page within a virtual address space of a particular process. In the terms of control bit, here we say the process that owns this page. And this field also includes flags such as valid, reference, modified, or protection and locking information. The control bits include flags and protection and locking information also. And the chain pointer, this field is always null, the index value of the next entry in the chain. Now, next we talk about the translation look-aside buffer, which is very important in virtual memory concept. So here in principles, every virtual memory reference can cause two physical memory access. The first, to fetch the appropriate page table entry and to fetch the desired data. So a straightforward virtual memory scheme will have the effect of doubling the memory access time. Now, to overcome this problem, most virtual memory schemes make use of a special high-speed cache for page table entries, usually called a translation look-aside buffer, or TLP. So this cache functions in the same way as a memory cache and contains those page table entries that have been most recently used. Now, we say the cache, memory cache, the whole goal is to increase the speed for the CPU to access data. So we know we can get data from main memory, but it's slower comparing to getting memory from the cache or the register. So again, each virtual memory reference can cause two physical memory access, one to fetch the page table entry and the other to fetch the data. And this takes time. So to overcome the effect of doubling the memory access time, most virtual memory schemes make use of special high-speed cache called the translation look-aside buffer. So the cache functions in the same way as memory cache and contains those page table entities that have been most recently used. So we have the diagram here, which explains the concept or the flowchart that shows the use of TLB, the concept of TLB. So the flowchart shows that if a desired page is not in main memory, the page fault interrupt causes the page fault handling routine to be invoked. And to keep the flowchart simple, the fact that the operating system may dispatch another process while this I/O is underway is not shown here. But by the principles of locality, we know most virtual memory references will be to location in recently used pages. Therefore, most references will involve page table entries in the cache. Because we can see in the diagram we start, we have the CPU to check the special cache called the TLB, or translation look-aside buffer. So check now, here we say the page table entry in the TLB. If it's no, then we have to access the page table. Is the page table in memory? If it's no, then we have to have the operating, if it doesn't have, then the operating system will instruct the CPU to read the page from disk. But if it's yes, then we update the TLB and then we continue. CPU generate the physical address and continue. So again, this flowchart tells us the whole concept of the special cache and the TLB. We start, CPU checks the TLB. If page table entry is in the TLB, yes, then we go straight and continue. CPU will generate the physical address of it. But if it's not, then we have to access the page table. Now, if the page table is in the main memory, then we update the TLB and continue. If it's not in the main memory, which means the operating system will do what? Instruct the CPU to read a page from disk. Since it's not in the main memory, we have to read it from secondary storage device. Then the CPU activities CPU will activate the input-output hardware. Then the page transfer from disk to main memory. And if the main memory is full, then we perform the page replacement. If not, we have the page table updated. Also, we have the concept of associative mapping. And here we say that the TLB only contains some of the page table entries. So we cannot simply index into the TLB based on the page number, because each TLB entry must include the page numbers as well as complete page table entry. As we see also, the flowchart shows the use of TLB. Now, there are a number of additional details concerning the actual organization of TLB. Because TLB contains only some of the entries in a full table, we cannot simply index into the TLB page on page number. Instead, again, each entry in the TLB must include the page number as well as complete page table entry. The processor is equipped with hardware that allows it to interrogate simultaneously a number of TLB entries to determine if there's a match on page number. Again, this technique is what we refer to as associative mapping, and is constructed with a direct mapping or indexing used for lookup in the page table. Also, we should know that the design of TLB also may consider a way in which entries are organized in the TLB, and which entries to replace when a new entry is brought in. And this issue must be considered in any hardware cache design. Now, we also have the page size. Here we say the smaller the page size, the lesser the amount of internal fragmentation. So here there are several factors to consider. One is the internal fragmentation. And as we said, the smaller the page size, the lesser is the amount of internal fragmentation. Now, to optimize the use of main memory, it's good for us to reduce the internal fragmentation. On the other hand, the smaller the page, the greater is the number of pages required per process. Because if we have smaller pages, then we will get more pages. So more pages per process means larger page tables. Now, for large programs in a heavily multi-programming environment, this may mean that some portion of the page tables of active process must be in virtual memory, not again in the main memory. So finally, the design issue of page size is related to the size of physical main memory and also the program size. At the same time that the main memory is getting larger, the address space used by the application is also growing. The trend is most obvious on personal computers and workstations, where applications are becoming increasingly complex. Furthermore, contemporary programming techniques used in large programs tend to decrease the locality of references within a process. So object-oriented techniques encourage the use of small program and data modules with reference scattered over a relatively large number of objects over a relatively short period of time. So again, design issue of page size is related to the size of physical memory and also the program size. So main memory is getting larger, then the address space used by the application is also growing or getting larger. And next we talk about, again, segmentation. And as we said earlier, segmentation allows the programmer to view memory as consists of multiple address space or segments. Now we have a couple of advantages as stated here. It simplifies handling of growing data structures. Also, it allows programs to be altered and recompiled independently. Also led itself to sharing the data among process, and also led itself for protection. So segment may be of unequal, and as they are not equal, or indeed more dynamic in terms of size. Memory references consist of a form of address, the segment number, and also the offset. Also, we have the segment organization. And the concept here is each segment table contains starting address of corresponding segment in main memory and also the length of the segment. So here we can also say that if a programmer doesn't know ahead of time how large a particular data structure will become, then it's necessary to guess unless we have a dynamic segment size is allowed. And this will simplify the handling of growing data structure as the size will be getting bigger. But if the whole concept uses a dynamic, which means during the runtime, memory will be needed, then that's a very good, good result. So we said, again, if a programmer doesn't know ahead of time how large a particular data structure will become, how large it will be, or how many memory size will be needed, then we don't know that. So it's necessary to guess. We have to guess it, unless if we are using dynamic segment sizes, which means the size can be changing during the running time or during the execution. So with a segmented virtual memory, the data structure can be assigned its own segment, and the operating system will expand or shrink the segment as needed. So this happens during the execution time. Now, if a segment that needs to be expanded is in main memory and there is insufficient room, then the operating system may move the segment to a larger area of a main memory. Then if it's available, that's it, if it is, or swap it out if it's not. The enlarged segment will be swapped back in at the next opportunity. Also, the concept allows programmers or programs to be altered and recompiled independently. Also. Now, next will be combining both paging and also segmentation. So in the discussion of a simple segmentation, we again indicate that each process has its own segment table. And when all of its segments are loaded into main memory, then the segment table for a process is created and loaded into main memory also. Now, if each segment table entry contains the starting address of the corresponding segment in a main memory, as well as the length of the segment, now the same device segment table is needed when we consider a virtual memory scheme based on segmentation. Again, it's very typical to associate a unique segment table with each process. And in this case, however, the segment table entries become more complex because only some of the segments of a process may be in the main memory A bit is needed in each segment table entry to indicate whether the corresponding segment is present in main memory or not. Now, if the bit indicates that the segment is in the main memory, then the entry also includes the starting address and the length of that segment. Now, both paging and segmentation have their own strength. Paging is more transparent to the program or to the programmer, and that's paging. Also, paging eliminates external fragmentation and also provide efficient use of memory. In addition, because the pieces are in, move, and out of the main memory of a face equal size, it's very possible to develop a sophisticated memory management algorithm that will explore the behavior of a programs, as we again shall see later on in the future lectures. Now, segmentation, in other hand, which is again visible to the programmer, also has a strength listed earlier in our table when we started. And this includes the ability to handle growing data structure, modularity, and support for sharing and protection. Now, to combine the advantage of both, some systems are equipped with processor, hardware, and operating system software to provide both against segmentation and paging. So in combining paging and segmentation system, a user's address space is broken up into a number of segments as at the discretion of the programmer. Now, each segment is in turn broken up into a number of face-size pages, which are equal in length to the main memory frame. Now, if a segment has a length less than that of a page, then the segment will occupy just only one page. Now, from the programmer's point of view, a logical address still consists of a segment number and also the segment offset. But from the system point of view, the segment offset is viewed as a page number and page offset for the page within the specified segment. So again, in our previous table, we begin with, we saw the difference, advantages, or the issue between paging and segmentation. And so if we combine both advantage together, again, we have some operating systems that again use both paging and segmentation in the virtual memory process. Now, next is the protection sharing. Here we see again the segment can lend itself to the implementation of protection and sharing policy. Again, the segmentation or segments can lead itself to the idea of implementation of protection sharing the system. Now, the reason is this because each segment table entry includes a length as well as a base address. A programmer cannot inadvertently access a main memory location beyond that limit of the segment. Now, to achieve sharing, it is possible for a segment to be referenced in the segment table of more than one process. So the same mechanism are, of course, available in the paging system also. However, in this case, the page structure of programs and data is not visible to the programmer. Now, making the specification of protection and share requirement kind of more awkward. So this will be the end of our lectures on the virtual memory, and wish everybody the best. If you have a question, you can post it in the canvas or send an email. Thank you.